So this video is on the differentiability of polynomials. So the aim for this video is to see that polynomial functions are going to be differentiable everywhere on the real line, and in fact that they're going to be infinitely differentiable everywhere on the real line. So we're going to start with two special cases, which are constant polynomials and the polynomial f of x is equal to x. And we're going to see how those two cases are going to be differentiable over the entire real line and are going to be infinitely differentiable over the entire real line. And then we'll see how we can use these facts along with the linearity of differentiation and the product rule to extend our conclusion to all polynomials. So let's begin then with constant polynomials. So f of x is equal to some constant value. So this is a function that's defined on the entire real line, and it's a real valued function. Now, the range is very small, it's just a single value. K is a real number, so every single element here is being mapped onto a single value in the codomain. And of course, graphically, these functions are extremely simple. They just look like horizontal straight lines where the level that the line is at in the y-axis is just the value of k. So in the case of this picture, k is a positive number, but if k was a negative number, it would be down here. So let's understand then why this function is going to be differentiable everywhere and indeed infinitely differentiable everywhere. So let's start with differentiable everywhere. So taking some random point in the real line, in the domain, let's see why the function will be differentiable there. So if it's differentiable there, it means that the limit of the difference quotient must exist. So the limit as t approaches x of f of t minus f of x over t minus x, this must exist in order for the function to be differentiable there. Now, remember, t is not allowed to equal x, but it's allowed to be any other point in the domain here, which is the real line. And for all of those values, f of t and f of x are going to equal the same thing because it's just a constant function. So this is going to be equal to k, and this is going to be equal to k, and therefore the numerator in the difference quotient is always going to equal 0. It's going to be then divided by t minus x. So on my picture here, this might be t here. And t minus x is going to be some number that's not 0. It will be a positive number if t is on the right-hand side of x, and it will be a negative number if t is on the left-hand side of x. So this difference quotient then is just 0 divided by some number that is not 0. And that, of course, is still just going to equal 0. So actually, if we were to plot the value of the difference quotient on our graph, it would look like this. What I'm drawing now in red, it would be 0, 0, 0 for all these values of t. Then it wouldn't be defined for t is equal to x, so we'd have to draw a hole there, and then it would be 0 for all of the values of t to the right of x. So it's just a function that looks like a horizontal straight line at the level of 0. It looks like the constant function f of x is equal to 0, except that it's not defined at the value x. We're then asking what is the limit of this function as t approaches x. Well, hopefully you can appreciate that that limit is going to be equal to 0. The whole function is just 0 everywhere, so as you get closer and closer to x, the value of the function gets and stays indefinitely close to 0. 0 is the value that you would expect the function to have there. It's where the hole is in the graph. So this limit does exist, and it's going to equal 0. And of course, there was nothing special about this x here. This argument holds true for any x in the real line, so the function is going to be differentiable everywhere in the real line, and the derivative is going to be equal to 0. So we can then view the first derivative itself as a function now, mapping the entire real line onto the real line, and it's also a constant function. It maps every real number onto 0. For the same argument that we've just used, we can differentiate this everywhere. Because 0 is a constant, this argument holds equally well for k is equal to 0. So it's also going to be true that whatever real number you pick in the domain here, that the first derivative viewed as a function over that domain is going to be differentiable everywhere, and it's going to have derivative value 0. So the second derivative, therefore, of the function is going to exist everywhere, and it's going to be 0 everywhere. And then this can be viewed as a function over the entire real line. Again, it's a constant function, therefore it's going to be differentiable everywhere. and it's going to have derivative value 0, and therefore we can say that the third derivative of the function is going to exist everywhere, and it's going to be 0. And you can continue this on. The fourth derivative will exist everywhere, and it will have value 0, the fifth derivative, etc. So constant functions, they are differentiable everywhere, and they are then infinitely differentiable because their derivative is also going to be a constant function over the entire real line. Now let's look at the other special case. So we'll look at the function f of x is equal to x. So again, this is a function defined over the entire real line, and it's a real valued function. This time the range of the function is going to equal the entire real line, and graphically it's also going to be a straight line, but it's now going to be inclined at an angle 45 degrees going through the origin like so. So we want to understand why this function is also going to be differentiable over the entire real line and why it's going to be infinitely differentiable. So let's start off with why it's differentiable over the entire real line. So again, take a general point x and understand why is it differentiable at that point. So for it to be differentiable there, it must be the case that the limit as t approaches x of f of t minus f of x over t minus x, this must exist. So now substituting in here what our function actually is, so f of t is just going to be equal to t, and f of the point x is going to equal x, so this becomes the limit as t approaches x of t minus x over t minus x. Now again, we don't care about when t actually is equal to x. The difference quotient is never defined when t is actually equal to x, but for all other t's that aren't equal to x, all of these t's to the left and all of these t's to the right, this is going to be defined and this is going to cancel. So the t minus x in the numerator cancels with the t minus x in the denominator, so it's equal to 1. So drawing this on the graph, if we were to plot the value of our difference quotient for all the values t, it would look like this. It would be 1, 1, 1, then it wouldn't be defined at t is equal to x, and then to the right it would be defined again, and for all values it would be 1. So that's level 1 there. So this function, this constant function, its limit is going to exist. As you get closer and closer to x, you can see that the place you would expect the value of the function to be, where you would have to put its value to fill in that hole there, it's 1. The function is just 1 everywhere, so as you get closer and closer to x, the value of the function gets and stays indefinitely close to 1. So this limit does exist, and it's equal to the value 1. Now again, there was nothing special about this point that we chose here. This argument holds true for all x's in the real line, so this function f of x is equal to x is differentiable everywhere over the real line and has derivative 1 everywhere. Viewing that first derivative now as a function over the entire real line itself, it is a constant function. It maps the entire domain onto the value 1. It is therefore going to be differentiable everywhere over the real line because of what we've just talked about, how constant functions are going to be differentiable everywhere over the real line. So that means that our original function is now going to be twice differentiable everywhere over the real line. We know that the value of the derivative of a constant function is going to be equal to 0 everywhere, which means that then the second derivative of our function is going to be 0 everywhere over the real line. It itself is therefore a constant function, therefore it can be differentiated everywhere, and we therefore can conclude that our original function is 3 times differentiable. Of course, its derivative will be 0 everywhere, so the third derivative will then be a constant function over the entire real line, and our argument then goes on. It's infinitely differentiable over the entire real line. So that then is the 2 special cases finished. We now want to turn our attention to general polynomials, and we want to prove that a general polynomial is 1, going to be differentiable everywhere over the real line, and 2 is actually going to be infinitely differentiable everywhere over the entire real line. So to do this, we're going to split it into stages, and the first step that we're going to do is to consider a polynomial of the form x to the power of n, so quite a simple polynomial, where n is a natural number, so 1, 2, 3, 4, 5, a counting number. And we want to show that this is going to be differentiable over the entire real line, so diff over r is how I abbreviate that. and that the value of its derivative at a point x is given by the formula nx to the n minus 1, so the familiar formula from calculus. So we already know that this is true in the case that n is equal to 1, and indeed we're going to do this as a proof by induction, so n is equal to 1 is going to be our base case. So why is it true when n is equal to 1? Well, when n is equal to 1, this is just the function f of x is equal to x. We know that that is differentiable everywhere over the entire real line. It's the special case we've just looked at. And then it is true that this formula holds true for n is equal to 1, because putting it in here, you get 1x to the power of 1 minus 1, which is 0, which is just 1 for all x. So that means that the value of the derivative everywhere is just 1, which we know is true. That's the value of the derivative of the function f of x is equal to x. So we have our base case. The theorem is true in the case n is equal to 1. What we now want to prove is that if it's true for n is equal to k, it implies that it is true for n is equal to k plus 1. And then because it's true for n is equal to 1, if we've got this, we'll know that it's then true for n is equal to 2, using k is equal to 1, and then because it's true for n is equal to 2, using k as 2, we'll know it's true for n is equal to 3, and then so on. So by induction, we'll know that it's true for all natural numbers. So we then need to show that this step, the inductive step, is true, that if it's true for n is equal to k, it implies that it's true for n is equal to k. So we're allowed to assume that it's true for n is equal to k, so we'll assume that if we have the function f of x is equal to x to the power of k, that this function is differentiable over the entire real line, and that its derivative is given by this formula here. Now let's consider x to the power of k plus 1. How do we know that this is going to be differentiable everywhere over the entire real line, and that its derivative is going to be given by the relevant formula? Well, we're going to use the product rule and split this into x to the power of k times x. So let me just remind you of what the product rule says. So the product rule says that if you have two functions, f and g, that are real valued functions over some domain of the real line, and they're both differentiable at some point, let's call it x, in your domain, then if you construct the new function, the third function, by producting f and g together, then this product function will also be differentiable at your point x, and its derivative at that value, x, will be given by f prime g plus f g prime. So the value of the derivative of f at x times the value of the function g at x plus the value of the function at x times the value of the function f at x times the value of the derivative of g at x. So we can split x to the k plus 1 into x to the k times x. We could view this as our f and this is our g. Now, by our assumption, we got to assume that this was true for n is equal to k. We therefore know that this function x to the power of k is differentiable over the entire real line, and we know that its derivative, so f prime at x, is given by kx to the k minus 1. Looking now at g, we know from our special case that g is differentiable over the entire real line, and that its derivative, so g prime for any x, is equal to 1. Now, by the product rule, because these are both differentiable over the entire real line, that means that the product of the two is going to be differentiable over the entire real line, and that its derivative is going to be given by our product rule formula. So plugging that in, we've got kx to the k minus 1 is f prime at x, times g, which is just equal to x, plus f at x, which is x to the power of k, times g prime, which is 1. So simplifying this, so x to the power of k minus 1 times x is just x to the power of k, so this gives us the derivative of our function x to the power of k plus 1 is k plus 1 times x to the k, which is what you would have expected it to be for this formula here. So if you put this into this formula, you'd get k plus 1 times x to the power of k plus 1 minus 1, which is x to the power of k. So what we have shown is if it's true that this one is differentiable over the entire real line and that its derivative is given by this kx to the k minus 1, then you can conclude that this one, x to the k plus 1, is differentiable over the entire real line, and that this formula does hold true for it as well. Its derivative is k plus 1 x to the k, i.e. this formula. So we've shown that this being true for n is equal to k implies that it's true for n is equal to k plus 1. We've completed the inductive step, and then, as I say, because it's true for n is equal to 1, it's now guaranteed to be true for n is equal to 2, guaranteed to be true for n is equal to 3, etc. So we know now that this is true for all natural numbers, that if you have f of x is equal to x to the power of n, this simple polynomial will be differentiable over the entire real line, and its derivative will be given by this. So now we're going to move on to general polynomials. So we're going to show that a general polynomial function is going to be differentiable over the entire real line, and we'll find what its derivative is equal to as well. So f of x now is going to be a general polynomial, and I'll write this as follows. So we'll call the coefficients c's, and we'll subscript them by what degree term they're in front of. So c0 is the constant term, plus c1x plus c2x squared, plus, and then there'll be some highest degree term, which we'll call the nth term, and it can have coefficients cn, so cnx to the n. So this is now our general polynomial function. Now, note some of these coefficients below the cn coefficient, these might be 0. So for example, c2 could be equal to 0. There might be no x squared term in our polynomial. That's absolutely fine. So some of these lower terms might have 0 coefficients. So what we want to prove about this then is that it's going to be differentiable over the entire real line, and that its derivative is going to be given by, I'm going to write 0 there, which is what this constant term differentiates to, plus c1 plus 2c2, so this is just the formula from familiar calculus, plus all the way up to n cn x to the n minus 1. And note that this formula still works regardless of the fact that some of these coefficients might be 0. So for instance, if c2 had been 0 and this polynomial had no quadratic term, then this c2 is still here. It will get rid of this linear term in the derivative. It's going to go to 0. So it doesn't cause a problem. So the way we're going to prove this theorem is by strong induction, and we're going to firstly consider two initial cases that are going to be our base cases. Now, we're going to consider constant polynomials and degree 1 polynomials, so degree 0 and degree 1 polynomials. We're going to do them first of all. Now, it isn't completely necessary to have both of them as our base case. We could just take degree 0 polynomials as the base case and then do the inductive step. However, I think it's helpful to look at degree 1 polynomials because it's going to illustrate the key principle that's going to allow us to prove this by strong induction before we then have to apply it in a more complicated scenario. So let's look at both degree 0 and degree 1 polynomials as our base case. So degree 0 polynomials, these are just constant polynomials, so all of these are gone now. It's just c0. c0 could be a non-zero real number, or indeed it could be 0. It could be the constant polynomial that maps everything onto 0. In that case, we already know that that function is going to be differentiable over the entire real line, and then looking at this formula is going to be fine as well. All of this goes, because all these are 0, and then we're just left with 0, and we know that constant polynomials, all of them, differentiate to 0. So this formula is right for those degree 0 polynomials, and that's why I insisted on writing the 0 here, so that when all of these are gone, there's still something written here. Now, let's have a look at degree 1 polynomials then. So let's consider f of x is equal to something of the form c0 plus c1x. Now, of course, c0 could be 0, in which case this is still a degree 1 polynomial, but more generally it might be non-zero. So we want to understand why the theorem is true for these degree 1 polynomials. Why is this going to be differentiable over the entire real line, and why is this formula correct for its derivative? So its derivative should be c1 everywhere. So we're going to use the linearity of differentiation in this proof. So I'll remind you of what this says. So it says if you have two functions, g and h, that are both real-valued functions defined over some subset of the real line, and they're both differentiable at some point, which we'll call x, then you can construct a new function by taking a linear combination of g and h, so a function like this, lambda 1 times g plus lambda 2 times h, where both lambda 1 and lambda 2 are just constants, so they're just real numbers. And this new function, this linear combination function of g and h, this is also going to be differentiable at x, where both the two initial functions were differentiable, and its derivative is then going to be lambda 1 times the derivative of g at x, plus lambda 2 times the derivative of h at x, lambda 1 g prime plus lambda 2 h prime. So a result that should be very familiar from calculus, but which we prove in an earlier video in this playlist on real analysis. And we're now going to apply this theorem here to this degree 1 polynomial. So we're going to split this into two functions. So we'll call c0, this can be our g, x is going to be our h, and c1, that's just a constant, so that can take the place of lambda 2. Now we don't need lambda 1 in this example. You could view lambda 1 as being 1, if you like. So g, this is just a constant function then. We know that this is differentiable over the entire real line, and we know that its derivative everywhere is going to be equal to 0. H is just the function h of x is equal to x. We know it's going to be differentiable over the entire real line, and we know its derivative everywhere is going to equal 1. So because g and h are differentiable over the entire real line, you can then conclude that this linear combination of g and h is also going to be differentiable over the entire real line, i.e. this degree 1 polynomial is differentiable over the entire real line. And note, this still holds true even if c0 was 0. 0 counts as a constant function, it's differentiable over the entire real line. So this really is absolutely fine what we're doing here, concluding that this is differentiable over the entire real line. And what's the value of its derivative going to be equal to? We'll now just apply the rule. So it's lambda 1 times g prime. Lambda 1 is kind of 1, so 1 times 0, 0, so that doesn't contribute. H prime is 1, lambda 2 is c1, so it's just going to equal c1. So that means that this formula is correct for degree 1 polynomials. So our theorem is absolutely fine for degree 0 polynomials and degree 1 polynomials. So now let's do the strong inductive step. So this time it's not enough to just assume that it's true for degree n is equal to k. We need to assume that it's true for degree n is less than or equal to k. So k is some natural number, it could be 5, and your induction is relying on it being true for all degrees less than 5. So from 0, 1, 2, 3, 4, 5, it would be true for all of them. Of course, it's not true for the negative numbers, it's only the natural numbers. So for all n is a natural number, so from 0 upwards, it is going to be assumed to be true. So we're going to show that if it's true for degree n is less than or equal to k, you can then conclude that it's true for n is equal to k plus 1. So then because it's true for n is equal to 0 and n is equal to 1, you're then able to conclude that it's true for n is equal to 2. Because it's then true for 0, 1 and 2, it will then be true for 3. Because it's true for 0, 1, 2 and 3, it will then be true for 4, etc. You can conclude it's true for all k's are natural numbers. So the theorem will be true for all degree polynomials. So let's now consider then a polynomial of degree k plus 1 and see how, by assuming the theorem is right for polynomials of degree k or less, we can show that it will be true for this polynomial of degree k plus 1. So we'll have our polynomial here, c0 plus c1x plus, and then we'll go all the way up to ck x to the k. Now, of course, ck could be 0, and then we've got ck plus 1 x to the k plus 1. So what I was just saying is that this term that's just 1 lower than the highest degree term, it might have coefficient 0. That's absolutely fine, but in general I've put ck there. So we now want to prove that our theorem is going to be true for this. So the way we're going to do this is we're going to split it up into two parts and apply the linearity of differentiation. So we can view this part as our g function in the linearity of differentiation, and we can view this part as our h function, and then this value here is lambda 2. Now, by the inductive assumption, looking at this g, this is a polynomial of degree less than or equal to k. If ck is non-zero, then it's a polynomial of degree k. If it's 0, then you need to keep going down and find the first term that doesn't have a coefficient of 0, and it's then that degree. But its degree is certainly less than or equal to k. So we know that the theorem is going to be true for that polynomial, i.e. it's going to be differentiable over the entire real line, and this is what its derivative is going to be equal to. So let's write that out. So g prime is going to exist for all real numbers, and it's going to be 0 plus c1 plus 2c2x plus all the way up to k ck x to the k minus 1. And again, I will emphasize that this formula is still going to hold true even if that ck is equal to 0, because it'll just cancel it out here equally. Now, then let's have a look at h. We can now use our previous theorem that we showed. We know that polynomials of this simple form are going to be differentiable over the entire real line, and we know that their derivatives is just going to be k plus 1 x to the k. That's what we showed in the previous theorem that we proved with normal induction. Therefore, because g and h are going to be differentiable both over the entire real line, you can then conclude that this linear combination of the two is also going to be differentiable over the entire real line. So that's the first part proven. And now we can say what its derivative is going to be equal to. And by the way, I just want to stress, the reason we need strong induction is because we don't necessarily know that this is a degree k polynomial. That's where we were using the fact that it was true for all degrees less than or equal to k, because this might have been 0, and therefore we needed the fact that it was true for one of these degrees lower than k. Anyway, back to where we were. So let's work out now what the derivative of f is going to be everywhere. So it's going to be lambda 1 is kind of 1, you can view it as, so it's just going to be g prime, so this part 0 plus c1 plus 2c2x plus all the way up to k ck x to the k minus 1, and then it's going to be plus lambda 2, which is ck plus 1, and then times h prime at x, which is k plus 1 x to the k. But of course that formula that we've got here is now our exact formula from up here, so therefore our polynomial of degree k plus 1 is satisfying both parts of this theorem. It's differentiable over the entire real line, and its derivative is going to be given by this formula. So by induction we can now say, because it's true for degree 0 and we also showed degree 1, we can now conclude it's true for degree 2 and then degree 3 and then degree 4. Indeed, it's true for all degree polynomials. So what we have overall proven here then is that any polynomial function is going to be differentiable over the entire real line, and its derivative is itself going to be a polynomial function over the real line. Therefore, you can conclude that it's going to be infinitely differentiable over the real line, because consider now its derivative. This is going to be differentiable everywhere over the real line because it itself is a polynomial, and we've just proven that all polynomials are differentiable over the entire real line. And then the second derivative, i.e. the derivative of the derivative, that's also going to be a polynomial because we've just proven that any polynomial, its derivative is going to be a polynomial. So using this over and over again, you can then see that any polynomial function is going to be not only differentiable over the real line, but because it differentiates to another polynomial function, it's therefore going to be infinitely differentiable over the entire real line. And with that, we will finish this video. Thank you for watching.